So we spent the first day looking at some of the fundamentals of engines. Second day, yesterday, talking about some of the details of the models that are embedded in CFD codes used to study engines. And today we'll talk a little bit more about applications. And we'll use those models to look at diesel, spark ignition. And then we'll talk about some advanced engine concepts, including low temperature combustion. And then we'll talk a bit about the future. Okay, so let's start off with a discussion about diesel engines. As you know, diesel engines are ubiquitous. We use them pretty much for all the heavy lifting in our society. And we come with some examples of diesel engine applications here, whether it be on-highway, marine, power generation, locomotives, pretty much everything. They even use them in nuclear power stations. Why? Well, it's the backup in case something goes wrong. And as you know, in Japan, those engines were flooded, so they didn't even have the backup, which was a disaster. Okay, diesel combustion overview. As we've discussed the first few moments of this course, the air is drawn in and compressed through the valves here. Fuel is injected into this high temperature, high pressure environment as a result of the compression process. The load is controlled by controlling how much fuel you inject into the engine. And when all is said and done with conventional diesel combustion, you have a very heterogeneous mixture of fuel and air in the mixture, in the cylinder. So you have a wide range of concentrations going from just pure air in some locations in the chamber to very dense liquid spray regions where the equivalence ratio, for example, can be very high. So diesel engines operate over a wide range of air-fuel ratios, going from idle all the way to full load. And as we discussed briefly, there's a wide range of size of diesel engines, going all the way from sort of marine engines, 900 millimeter type of bore, all the way down to 80 millimeters or less for the light-duty type engines. This slide also points out that a typical design feature is that the large engines are what I call quiescent, in the sense that they have relatively low swill induced by the intake system, whereas for light-duty engines, you typically have high swill, especially for starting the engine, to try to get the fuel and the air to mix. So some of the other parameters you can see here in this table that characterize these different types of sizes of diesel. There are some sort of guidelines if you were to design a diesel engine that you have to respect. And these have been learned over the years. You know, diesel is over 100 years old, right? Rolf Diesel started designing his engines in the 1890s. What people have learned is it's a good idea to center the fuel injector in the combustion chamber, and preferably to have it centered within the piston bowl, because if you're doing the injection near top dead center, you want to have as symmetric a flow field as possible to prevent issues that would come from non-uniformity of the pressure release. You want to supply the air, as we mentioned, sufficient to have enough oxygen available to prevent smoke at high load. Some of the parameters that you're interested in would be how do you inject that fuel, what is the rate with which the fuel is injected, the intake geometry that light-duty engine, for example, might favor the production of swill. You're interested in the boost pressure and whether you use that charge air cooler to get the temperatures under control when the intake valves close inside the combustion chamber. Compression ratio is a design parameter that's important. How much exhaust gas you recirculate to try to dilute some of the incoming air. In terms of the injector itself, when do you inject the fuel? What size injector nozzle holes should you use? And what is the best orientation of the spray angle? In terms of the piston design, what type of piston do you want? Do you want one that features a central pip here? Do you want one that has the so-called reentrancy? This region above the piston called the squish region or rim here. What should the extent of that be? What's the best design of the bowl? The bowl is basically there to try to confine the fuel and in some sense to keep it away from the liner, because you don't want to inject fuel against the liner because that can interfere with lubrication. So a lot of design parameters for optimal design of diesel engines. And all is said and done, there are several constraints. For example, you cannot exceed a certain peak pressure in the engine, otherwise it'll blow apart. You also have to worry about limits on the fuel injection pressure. So a lot of work has been done over the years, and at the Sandia National Labs, John Dick, some years ago, proposed a conceptual model of diesel spray combustion that changed the way people thought about diesels. So these are some images from one of his papers here that show the liquid fuel being injected, the liquid fuel penetrating into the combustion chamber from one of the spray plumes. And at a certain moment, the liquid length reaches its maximum, as we discussed last time. The vapor continues to penetrate. And you start to see the development of, he calls them PAHs here, but precursors. And then a flame is established. This thin line you see here is a diffusion flame. And then eventually soot starts to be produced, starting from those precursor species like we discussed last time. So in this graphical illustration here, you have liquid fuel, air being entrained due to the high velocity motion of that liquid. You have this kind of fuel preparation region here, a rich region where soot precursors are being formed and kind of a low temperature combustion products. And then finally, this region here where there's a shortage of air. There's still some entrainment, of course, but here's where you would see quite a bit of soot being produced. And this thin line you see here is the diffusion flame that separates the fuel region from the oxygen. If you look at the picture shown here, this is a typical heat release rate diagram. We kind of discussed this briefly once before as well, where you start injecting over here, so that's back here someplace, and at a certain moment combustion starts. So all the fuel that has already been injected has essentially spontaneously combusts, producing this very sharp premixed burn. The fuel and the air has had time to premix. And then following that, we have what's called diffusion burning, where now we rely on the transport of air into this fuel-rich region to establish a diffusion flame. So here's some pictures of diesel sprays. This is actually from Chuck Miller at Sandia. One of the things you notice, of course, is a lot of luminosity because of the soot, as we spoke about last time. And this is a picture of conventional diesel. You can kind of see the liquid here. It's still injecting. You can see where the flame is established, and then this downstream region where the soot is being produced. So one of the interesting ways of looking at engine combustion was actually proposed by Professor Komimoto. And he suggested that one could use, say, for a constant volume combustor and look at what happens if you have a homogeneous mixture at a certain equivalence ratio and at a certain temperature, and you leave it that way for some milliseconds, typical of the time of interest in the diesel engine. And what you can do by doing that type of calculation, using a CFD code or Chemkin or such a code that also includes a soot model, is create these sort of islands where, for example, at high temperatures and low equivalence ratios, you find a lot of NOx is being produced, whereas with high equivalence ratios, with very rich mixtures, a lot of soot is produced. And then with very lean mixtures and low temperatures, you find unburned hydrocarbons and CO. So this is a very nice map because if one knows, for instance, the local equivalence ratio at each point in this combustion chamber, you can kind of identify it back on this diagram, if you also know its temperature, and see whether there's a high propensity to make NOx, soot, or unburned hydrocarbons. But one thing that pops out immediately is that you can see there's a regime here where if you were able to operate here, you would have low NOx, low soot, and also very little unburnt fuel. So that's a very interesting area to operate in. And just to contrast that, if you look at conventional diesel starts with very rich mixtures at low temperature. That would be this region here, where the fuel is vaporizing, has not yet undergone significant combustion. And then the fluid packet would pass through this region and eventually mix with the air, so the equivalence ratio decreases and the temperature increases. So traditional diesel combustion covers the whole range, where essentially soot is being produced, CO is also being produced in regions that are at low temperatures, and then eventually nitric oxide is being produced. So to try to avoid that, people have come up with various ideas, and one of them is the so-called early injection premixed charge compression ignition, PCCI, where instead of injecting the fuel close to top dead center, you inject the fuel much earlier, like in this picture here, and you allow time to elapse so that those rich regions that were up here have time to mix with the chamber air and reduce the local equivalence ratios. By doing that, you can avoid much of the soot. So there's actually a different scale factor in these pictures here, but you see you still get some soot. It's formed more or less around the region near the edge of the bowl. But you have lower local equivalence ratios, and if you dilute this mixture, you can lower the peak temperatures. So if you use a lot of EGR, exhaust gas recirculation, you can lower those temperatures and operate in this regime. So you can see where we're headed. If we had a homogeneous charge, in other words, injected early enough that the mixture was completely homogeneous, we would have homogeneous charge compression ignition. We would run at a certain equivalence ratio, in other words, a certain fuel-air ratio. And as we compress the mixture, temperatures increase. At a certain moment, we would have combustion occurring. Since it's homogeneous, that would be pretty much instantaneous combustion or very fast combustion. But if we do things right, we can make it happen at the right time. It requires very good charge preparation, so we have a nice homogeneous mixture here. And we need to know exactly what the temperatures are, say at intake valve closure, so that taking into account the compression, we know just when that fuel is going to ignite and take off. Now, as we've discussed, there are limits to this type of combustion. If, for example, we try to run with richer mixtures, the pressure rise rate becomes very large, and because of that, we can have very high in-cylinder pressures, and that leads to problems. So HCCI is typically limited to lighter load operation. But we can stay inside this nice box here, avoiding NOx, soot, and unburnt fuel. So I mentioned John Deck's conceptual model. Here's a picture of it again. He used a variety of optical diagnostic techniques to establish this picture here. And one of the main conclusions is that the OH radical, which is kind of an indicator of the main or second stage of combustion, really only is located kind of in a thin sheet around the jet, as is characterized by a diffusion flame, as we already know. If one operates with low temperature combustion, in other words, like that PCCI we were talking about, things change a little bit. And Mark Musculus at Sandia has proposed a conceptual model. In this case, here's our fuel again. The light brown here is vapor that's being produced from the liquid fuel. And now this blue region represents basically intermediate species, such as formaldehyde, that characterize the first stage of combustion. All of that is kind of squeezed into this tiny region here in the conventional diesel. And here you see it actually fills out quite a large part of the diesel jet. And then as we move further downstream, we see the appearance of soot precursors and so on, and then finally soot at the tip in these roll-up vortices at the tip of the jet. And the other thing is, if you look at the OH itself, it is now not just confined to a thin region at the edge of the jet, but it's more or less everywhere inside the jet, especially in the green region here, where you've gone to this sort of second stage of combustion. So to try to see if our codes are able to capture some of these features of diesel combustion, here I'm going to show you some results with our code as Kiva, coupled with ChemKin for the detailed chemistry, and then the G equation model for flame propagation. So ChemKin basically is an ODE solver. You feed it the detailed chemical reaction mechanism or reduced mechanism. And in each computational cell, basically, it considers that cell to be a well-stirred reactor. You do the chemistry calculation, and you feed that back to the CFD code. The diesel fuel chemistry in what I'll show you today is modeled with a variety of mechanisms, but the baseline is using inheptane to represent diesel fuel. As a matter of fact, a lot of the experiments done at Sandia are done with inheptane because some of the laser-based techniques rely on fluorescence, and diesel fuel fluoresces all over the place, and so it's very difficult to interpret a fluorescence measurement unless you go to a fuel that essentially does not fluoresce itself, but the products formed from the fuel do fluoresce, so you can identify the stages of combustion that way. Anyway, so the flame propagation, if it exists, is modeled through the G equation that I discussed with you also. Spray is modeled with our spray models that we discussed yesterday. We use that gas jet theory near the nozzle to reduce grid dependency in the drop drag calculations. We have collision models with bounce, coalescence, fragmentation, and so on of the droplets. The Kelvin-Helmholtz-Rayleigh-Taylor breakup model. And then for the fuel properties themselves, we use tetradecane because it has a viscosity, surface tension, so on, those physical parameters, very similar to what would characterize diesel fuel, whereas the chemistry in these cases is inheptane. Here's a picture I showed you also last time of the experimental apparatus at Sandia. Essentially, here's the piston. It's a glass piston or quartz with a mirror and extended piston arrangement so that you can look up through the piston into the combustion chamber. Mark's engine also replaces one of the exhaust valves with a window. And then on the side here, the liner is also optically transparent. It's a quartz window. So you can shine a laser beam through the engine to illuminate the contents and then view that through either of these two windows. It's a Cummins N14 diesel engine base, so it's about a 14 millimeter bore. Some of the parameters shown here, the displacement's 2.3 liters. It has a relatively low compression ratio because basically with an optical engine and with all of these extended windows and so on, you're kind of stuck. So what they do to get realistic diesel conditions is they run with higher boost pressures and temperatures at intake valve closure to kind of simulate what you would have with a higher compression ratio by the time you reach top dead center. Here are just some more details about the sprays, the nozzles, and so on. So here's a couple of interesting conditions that one of my students, Sepius Singh, looked at with Mark at Sandia. We're interested in comparing high temperature combustion and low temperature combustion. So he arranged a high temperature combustion with a short ignition delay, and that was done by running with quite a high intake temperature, so that by the time you compress the mixture up to TDC, the temperatures are such that you get a very fast ignition. Alternatively, there's a high temperature combustion regime, high temperature because we don't use any dilution of the oxygen, so there's just natural air here. Longer ignition delay because the intake temperature is reduced. And then finally, for the low temperature combustion, essentially you can see the oxygen concentration has been reduced significantly. That corresponds to about a 50% or 45% exhaust gas recirculation strategy. So because of all that diluent, the temperatures are going to be much lower. And you can see the predicted adiabatic flame temperature for these conditions would be 2,700 for these two cases, and only 2,200 for the low temperature combustion case. You can see some of the other parameters here. It's 1,200 RPM, relatively light load, around 4 bar IMP. So 3 different conditions: high temperature combustion with long with short and medium ignition delays, and then low temperature combustion with a long ignition delay. So if we just look at the plots on the right here, just to get an idea of the combustion itself, we're comparing the experiment, the solid black line here, with the Kiva predictions, just with the chemical kinetics for combustion, and then including the G model to account for any flame propagation if it exists. And we'll talk more about that in a moment. So this is the high temperature combustion with a short ignition delay. This green profile, it looks like a parabola here, is the injection rate. So that's where the fuel starts being injected. And the end of injection, you can see the injections occurring about 5 degrees before top dead center. The other thing that you see here is the heat release rate. So we can see the evidence of that premixed burn and then the diffusion burn for this short high temperature combustion. Good agreement with the measured and predicted cylinder pressures. So when we go to a lower intake temperature and now longer ignition delays, you see injection again starting about 5 degrees before top dead center here. Here's the end of the injection. Combustion is delayed relative to what we saw here. And in fact, we see more of just a premixed burn because the fuel has had a lot of time to, or more time to premix, but there is still evidence of some diffusion burn. And then finally, for the long ignition delay case, or like the PCCI case, we start the injection about 20 degrees before top dead center. It's over by 15 or so. Then there's a significant dwell, and then we have ignition occurring. So here are the three different regimes. If we take a look at these pictures here, and they're a little bit hard to see, but you can look at them maybe in the notes as well. These two up here refer to the experiments. And there's two pictures. They're showing you the OH distribution, the hydroxyl radical distribution in the engine. And it's difficult to see, but as I said, if you look carefully, you can see that this OH is confined to a region around the jet in the case of the short high temperature combustion regime because of the existence of a diffusion flame. They're shown here at 6 degrees, 10 degrees, and 14 degrees. Well, I guess I'm looking here just for this case at 6 degrees after top dead center. Down here are the corresponding simulations. Oh, I should just mention there's two experimental data shown here, so-called online and offline. So by looking at a particular wavelength for emission, you can identify whether this is truly OH by having essentially very little emission in the offline position. So basically, we can say for sure that this is OH. If you look at the Kiva results, you see basically very similar results whether you use just the kinetics or the kinetics plus the G model. This purple stuff you see here, and I'm going to show blow-ups of these in a minute, is the location of the so-called flame predicted by the G model. But you can see again that the thin region of OH surrounding the jet like we see in the experimental data. On the other hand, when we go to the medium case, these OH regions tend to broaden. We see more a thicker region characterizing the combustion. And when we go to the long ignition delay case, this PCCI type combustion, the OH is pretty much everywhere in the jet. So those are characteristics that are seen in the experiment. And I want to just show you kind of a movie that demonstrates what the models are predicting. These simulations were done by Sage Cookjohn, one of my students who just graduated. So here we see the injection starting around -5. You can see here we are in time. Injection is still in progress. We're just at the beginning of combustion. You can just start to see the appearance of these broader regions around here. They correspond to formaldehyde being formed at the edges of the jet there. If we continue in time to 1 degree before top dead center, you see now the appearance of OH in these thin bands around the jets, and that corresponds very well with the experimental image. The experimental image is showing you 3 jets actually, so you're looking at this piece here, these two, and this piece in the image. And this is the time at which that's taking place. So OH is already starting to appear. And then we move on to top dead center. You can see this is developing. The other interesting thing is that now you see this red region here, which is acetylene. So this is the soot precursor that's starting to form in the interior of the jet. Here's your formaldehyde, and here's your OH. Let's see, we move on in time. This was at top dead center. Here we go to half a degree after top dead center, very similar looking image. Here we're at the sort of peak of the diffusion burn stage of combustion. And I think that's the last image. You can see we're just starting to reach the rim of the, this is the piston bowl edge here, and we started to spread out along the edge. OH, soot, no more formaldehyde visible. So basically the simulations and the experiments both show the existence of a diffusion flame that's about 1 millimeter thick for this high temperature combustion with a short ignition delay. And that agrees very well with John Deck's conceptual picture. I mentioned the G equation and the role of flame propagation was of interest. So if we turn on that model, what we find is that the G equation solution essentially predicts the location of the G equals 0 surface to be around the to be located around the OH field. So this gray region is the OH here. The colors here show the equivalence ratio. So inside the jet, we have very rich mixture along the G equals 0 surface. If you look at the flame speed for very rich mixtures, it's 0. So basically, this mixture here, this G surface, is not moving. Similarly, on the other side of the flame, we have very lean mixtures, indicated by blue here on the G equals 0 surface. And so, again, we have very low flame speeds over there. In fact, the only place where the flame speed is likely not to be small is right here at the tip where the equivalence ratio is around 1. And in fact, if we plot the turbulent flame speed along the flame surface here, we see that it's basically on the order of 100 meters per second or so right here at the liftoff location where the OH starts to be in evidence. So basically, this lifted flame, here's our liquid, here's where the flame is located. If you use a model like a flame speed model, it really only is doing anything in this region right where the flame is lifted. And in fact, you see OH even ahead of that. So you don't really need to consider this flame propagation at all in the case of diesel combustion, conventional diesel combustion. So, and that explains why we've been able to get very good results without having to consider flame propagation for many years by modeling diesel combustion as just a diffusional mixing with the K epsilon diffusion model of the fuel and the air and a chemical kinetics model where the fuel and the air meet. Okay, so if we look at the low temperature combustion case, so remember this is now where we have very early injection and then a long delay before combustion is evident. Here you see again a simulation. We've got injection occurring. You can see now the formation of formaldehyde, so low temperature combustion products that kind of spread all around. This is now right here in the low temperature combustion region, or the cool flame combustion as it's sometimes referred to. The liquid has now disappeared because we at the end of injection and it's more or less vaporized. There's a little bit of evidence of some liquid left, but it's vaporizing, and we're starting to see the first stage combustion. If we continue then in time, we see now the onset of second stage combustion. That's indicated by the appearance of OH, all this green stuff that you see here that came from the low temperature regions where the formaldehyde was located. And of course, these jets are all now striking the bowl wall And in that region, we see this red stuff, which is the soot precursor, the acetylene being produced. And if you got a good memory and think back to that PCCI picture I showed you before, you saw all of the luminosity was around the edge of the bowl for this PCCI, or low temperature combustion. So very consistent with what we're seeing in this picture here. As we continue the combustion, oh, and I should just mention, here's the experimental image. You see a lot of OH, just like we see in the experiment, in the calculation rather. And then if we go a little bit further, nothing much changes. And then finally, this is now at the end of this burn spike, if you like, this premix burn spike. And then finally we're done. So basically, because we have a lot of time for mixing, we saw the formaldehyde first, and then we saw OH, which pretty much filled the entire jet cross-section. So that's a big difference between high-temperature diesel combustion and low-temperature diesel combustion. Very consistent with Mark Musculus's conceptual model, where again, we said you could identify the first stage and the second stage combustion, and then the soot forming regions. And you can even see those soot regions associated with this vortex at the tip of the jet, just like in the model. So just to summarize then, what we see is that the flame structure really depends on how much time is available for mixing. For the short ignition delay, the diffusion flames are quite thin, 1 or 2 millimeters thick. It agrees quite well with the experimental data. For the high temperature combustion medium ignition delay case, we see fatter flames. The diffusion flames are in the 4 to 6 millimeters range. And we see that spreading of the OH in these OH PLIF images as well. And then for the long ignition delay, or the low temperature combustion case, the OH basically fills the entire jet cross-section, and that's also seen in the experiment. The reason there's this white box here, by the way, is that this is the region where the online and offline images from the PLIF are significantly different. So you can for sure say that this is OH, whereas out here it was more difficult because there is, of course, fluorescence from other species in the mixture as well. So what Mark and his group do is they kind of identify regions where they can for sure say there's OH, and sure enough, that's what we also see in the calculation. So the increase in this reaction zone thickness increases with mixing time. And the important thing is that we can capture this flame structure without considering turbulent chemistry interactions beyond what we have described, right? We have turbulence, which is entraining the air into this jet here. So turbulence is important from the standpoint of preparing the charge or mixing the air and the fuel. But the actual combustion itself occurs in this thin region where it's the chemistry that dominates. And we'll see that also a little bit more in a minute. Ignition occurs in regions where we have, obviously, premixed fuel and air. And as I just said, the combustion is controlled by large-scale mixing processes that are resolved in our RANS-type turbulence model. So we can conclude then from this study that reaction rates or reaction rate dependence on injection-generated mixing also decreases with increasing ignition delay. So the longer we have to wait before combustion starts, the more we forget about the injection, and the mixing process is more controlled by the background turbulence. If the ignition delay extends past the end of injection, combustion-generated mixing dominates versus injection-generated mixing. I'll show you that more in a couple of slides. The other interesting thing is the point was that the flame thickness varied for these different cases. And in fact, one can conclude that the flame thickness depends on, is identified by OH, and it really depends on the local equivalence ratios. So for example, for the high temperature combustion short ignition delay case in the simulation, we can plot the OH mass fraction contours and also the equivalence ratio. Inside the jet, the equivalence ratios are high, so we have rich mixtures as we expect. And at the edge here of this OH mass fraction contour, we have this number. And then at the other edge, the lean side of the flame, where the equivalence ratio is low, we can bound that as well and read off what the OH would be. And what we find is that essentially for this first case here, where we have 21% oxygen or air, OH is detectable in regions where the equivalence ratio is between about 0.2 and 1.6. If we look at the low temperature combustion case, we see here that we have richer mixtures in the central region of the jet, leaner mixtures obviously outside of that region where there's more air available. And again, the OH concentration kind of indicates the magnitude of the equivalence ratio. So essentially, the OH can be used to kind of estimate equivalence ratio in flames. And this is something that was proposed by Sapir in his thesis, and these results really confirm that. And basically, quantitative measurements of OH can be used to estimate local equivalence ratios. So OH, laser-induced fluorescence, can be used to estimate equivalence ratios. Okay, so getting back to the subject of turbulence and chemistry, this is kind of an interesting way of looking at it. Here we're looking at the high temperature combustion short ignition delay case. This line down here, this green line, again, is our injection rate curve. We start the injection, there's a short delay, combustion starts, and injection ends while combustion is still undergoing and continuing. Okay, so the black line that you see here is epsilon over k, which, if you remember from our discussion of turbulence models, is a characteristic time of turbulence, or turbulent mixing time. This is averaged over the combustion chamber. And you can see that it increases. Why does it increase? Well, because the injected jet creates turbulence. You have gradients in the mean flow that are generated from the injection, which create a production term in the K and epsilon equations that lead to the production of turbulence. So you can see this black curve rising here, even before we have significant fuel consumption. So FCR is the fuel consumption rate. The red, this blue curve here shows the heat release rate. And you see we have some, in this red region here, you can see fuel is being consumed, but it's actually going to those low temperature products like formaldehyde. So you don't see much energy release, but suddenly ignition takes place, as seen by the blue curve here. And we see a little bump in the kinetic energy, or the turbulence timescales here. That's associated with combustion-generated turbulence. And then, of course, everything dies away as we burn away the fuel. So that's what you see with the short ignition delay high temperature combustion. This is, again, just to remind you what that jet looks like at this time here, where we right after the ignition takes place. So kinetically controlled premix spike followed by mixing controlled energy release, as we saw before. So the turbulent mixing then is due to the injection event, and it stays elevated as long as we keep injecting, and then it dies away. As we expect, the rate of combustion is controlled by the rate at which we transport reactive material into the zone, the reaction zone. That's what our turbulence model does. Okay, so if we look at the medium ignition delay case, so now we have the injection over here. You see the turbulence time scale, the black curve. Turbulence is increasing now. You see the effect of the injection is such as to generate turbulence. And as the injection starts to end, this turbulence winds down, right? So as long as we inject, we are generating turbulence. when we stop injecting, the turbulence starts to die down. The blue curve here shows the heat release. So basically, at a certain moment near the end of injection, we start combustion. Again, the FCR is the fuel consumption rate. You see we're forming those low temperature products, but they don't release much in the way of energy. And then, as I said, we see this sudden onset of ignition. And notice what happens to the turbulence here. Big increase associated with the combustion event. So sharp increase in turbulent mixing due to the injection event. Injection event is almost finished by the start of combustion. But then we see a second spike in the turbulence due to the expansion of the hot products of combustion. And this occurs after a significant quantity of the fuel has already been consumed and formed into low temperature products. So basically, the spray-induced mixing is less important in this particular case. Ignition dwell, by the way, is the time between the end of injection and the start of combustion. So that's sometimes a confusing term. But basically, what you're trying to do in low temperature combustion is finish the injection before combustion starts. Finally, for the long ignition delay, low temperature combustion, here the injection, it's finished before any combustion takes place. Here's the turbulence associated with the injection event, increase there. And then here we see the low temperature combustion giving some mild heat release, and then a spike and a corresponding spike in the turbulence generated through the combustion, just like we saw before. So a sharp increase in turbulent mixing due to injection. Then we have the injection is finished before any second stage combustion. Fuel is consumed in two stages. You can see the low temperature combustion down here, and then the high temperature combustion. This high reaction rate is seen and is nearly completed by the time we have a second spike in the mixing rate. So turbulent mixing in this case appears to play a secondary role to the kinetics. Essentially, everything is happening right here. This is where all the heat is being released. And it's like a homogeneous charge compression ignition situation where you have suddenly very strong combustion. Okay, so those are the regimes of combustion for diesel engines, or diesel combustion. And what I want to talk now about briefly is spark ignition engines, because spark ignition engines are also pre-mixed combustion when we have port fuel injection, but direct injection when we have, or stratified combustion when we have direct injection, like in the examples shown here. So here's your spark plug, here's your fuel injector, you inject fuel. Sometimes it's redirected by the piston geometry. Sometimes you spray directly at a spark plug. In other cases, you use the piston to move the fuel to the spark plug. These are the so-called spray-guided and wall-guided configurations. And what I'm going to show you is just a few results from that engine that we discussed with the PFI last time. Now we're going to look at the direct injection case and see if we can understand some of the combustion. So here's a little picture showing the combustion domain. We have fuel injection, ignition. What I'm showing you here, this black line is the G surface that we discussed. That is for the propagating flame. Now the flame is propagating through a mixture with varying equivalence ratio that is established by that spray. Here's our spark plug, and here you see those spark kernels, the DPIC ignition model, and some details of the models here. This just gives a little confidence in those results. Shows the cylinder pressure and heat release curves as a function of crank angle from the experiments and the simulations for a variety of spark timings, 20 before top dead center, 24, 28, 32. We're able to capture those reasonably well for this stratified charge spark ignition case. This shows some of the other quite sensitive parameters, for example, nitric oxide versus spark timing. some discrepancies, but certainly the trends are calculated with these models. This one here shows the experimental unburned hydrocarbon from the engine and two different estimates of that from the model. Remember I mentioned that flame quench can be an issue when you're operating very lean mixtures, the flame propagation velocity goes to 0. And so in the model, we have a way of dealing with that. We look at the local turbulence length scales and compare that to the flame thickness estimated from the theory. And once it reaches some criterion, we say the flame speed goes to 0. So depending on this constant, CM3 here, we can get different estimates of how much fuel remains and has not burned because of the flame quench phenomenon. So you can see the results are quite sensitive to flame quench. There are other factors that are probably not very well modeled here. Namely, a lot of the unburnt hydrocarbon comes from crevice regions, the crevice region between the piston and the liner. That wasn't modeled in this simulation, so probably the difference here is, could be related to crevice hydrocarbons. So the role of turbulence in spark ignition engine combustion. We discussed the same slide I'm going to show you here last couple of lectures ago, so I'll show it again. This is for the premixed charge, or the port fuel injected case. We saw the pressure trace as a function of crank angle from the experiment and using the G model to describe the flame propagation. And we saw a pretty good agreement with the experiment. We also saw that if we turn off the G model and use only the chemistry to calculate combustion, in other words, rely on the chemical kinetics for combustion and the turbulence for the mixing, we find we're not able to match the data here. On the other hand, for the results I just showed you, where we have a direct injected engine, so we're injecting fuel, we're generating turbulence through the injection event. That turbulence is mixing the fuel and the air. Now it turns out the results are much less sensitive to the model formulation. So if we use the G equation, we got the results I showed you. The results are not that different if we just assume chemical kinetics controlling the combustion, like we saw in the diesel engine. So fuel injection essentially creates mixing, which enhances the flame speed. And that's shown also in these pictures here. Here we see the flame growth. If we just have the kinetics controlled model and compare that with the G model, here you saw significantly faster combustion. This was for the premixed case, the PFI case. So we can conclude then that auto ignition chemistry by itself is not sufficient to properly model flame propagation. So if you have an engine where flame propagation is the dominant mode of combustion, you cannot just rely on using chemical kinetics to describe combustion. So the turbulence enhancing effect on the flame propagation speed in premixed charge engines cannot be neglected. However, in direct injection engines, combustion is controlled by mixing rates, diffusion and combustion, or diffusion combustion. And so that's why with the diesel, we're able to do quite a lot of, and make a lot of progress without complicated turbulence chemistry interactions. Of course, the other thing to remember is if we go to HCCI type combustion, where the charge is homogeneously distributed, then you don't need to have a flame propagation model at all, because now it's just chemical kinetics that is determining combustion. So I also wanted to mention a little bit about knocking combustion, because let's say we have a flame propagating. As I showed you, we have detailed kinetics, or reduced kinetics models ahead of the flame and behind the flame. And it's possible to reach a situation where the charge ahead of the flame spontaneously auto-ignites. And in fact, you can see that in cylinder pressure data. Here's some cylinder pressure data taken in an engine where we have these different pressure transducer locations in our modeling. And I think the cylinder pressure transducer was at location 1 here. If you look at the cylinder pressure, you can see these wiggles. If you filter this data, and the filtering strategy is described here, you can just look at the AC component, if you like, of the pressure trace and get this wiggling looking trace that is associated with the oscillations in pressure. So how do you pick your range of frequencies? Well, classic paper from MIT in the 30s looked at the resonant modes in a combustion chamber and identified various modes. We'll see pictures of these in a minute, but there's centrifugal, radial and axial modes that have certain resonant frequencies that are shown here. So if you consider that, you can kind of filter out frequencies below 5 kilohertz and above 25 kilohertz, and this is the resulting figure. So the interesting thing here is this peak-to-peak amplitude of these oscillations, and that defines what's called a so-called NOC Index. You can define this in many ways. One way would be to average it over a number of cycles of engine operation. But in any case, what you're really looking at is the magnitude of this peak-to-peak pressure variation. So here shows some calculation results where what we looked at was the NOC index, this black here, as a function of spark timing for a premix charge engine. And you can see that if you go to very early spark timings, basically what you have is a situation where you've got a lot of preheating or compression of the gases ahead of the flame. They can undergo auto-ignition, leading to high NOC intensity. Whereas if you spark late, you don't have all that time for the gases ahead of the flame to be compressed and heat up, and so the NOC intensity decreases. This just shows pictures of the NOC intensity taken at this particular location in the chamber. Notice it's near the edge here, so the flame is ignited in the center of the chamber. It propagates out, and this is where you pick up NOC, or evidence of NOC. You see very strong NOC here for the early spark timings, and very light NOC for the later timings. So just to kind of get a picture of what's happening inside the engine here, here at the top is a severe NOC condition, and the bottom is a light NOC condition. You see at 10 degrees after the spark, the black line here indicates the G surface. The flame is just starting to get established. 20 degrees after the spark, here's the G surface. You can see the flame starting to propagate out. This white region that you see here is because we have a pent roof engine and we're taking a cutting plane through the engine, so ignore that. Then here's again the flame location, 25 after spark. Now you start to see something interesting. You see these red regions, which are high temperature regions, ahead of the location of the flame in the model. The G surface is back here. This region here is undergoing auto-ignition and raising the temperature locally. This is what is leading to the NOC. In other words, combustion is going faster than the flame. Similarly, the propagating flame. Similarly, for the light load NOC, the light knocking condition, here you can see you don't have many regions where the red region outpaces the flame propagation. So this is something that's very critical for the design of spark ignition engines. There's a lot of technology behind trying to avoid NOC, one of them being the use of high-octane fuels, for instance, to prevent that auto-ignition ahead of the flame. We've recently done, Xi Wang is a postdoc working with me, recently done a little bit more analysis of this. He looked at a very simple geometry, a pancake combustion chamber with a spark in the middle, and looked at flame propagation with different PRF fuels. So he basically changed the octane number of the fuel. And if he went down to a fuel with a low enough PRF number or octane number, he was able to generate really accentuated pressure oscillations in the combustion. Notice there's 3 different curves here. They correspond to the use of 3 different time steps in the simulation. So you need very small time steps in order to catch these high-frequency waves. Here's Draper's resonant modes again. You see there's kind of a sloshing mode here. Then there's a mode where you have basically side-to-side oscillations. Here are the radial modes, and so on. And each of these corresponds to a different frequency component of these oscillations. So we took our calculated pressure trace here, passed it through an FFT, and got this plot here, which basically shows where the energy is located in frequency space. And you can see there's quite a lot of energy here associated with this third circumferential mode at around 15 kilohertz. These other bumps correspond to these other modes. It's kind of hard to imagine what's really going on here. So he made a movie, which is probably even harder to imagine, but this is, at least it's exciting to look at. What you're seeing here is the temperature associated with the sloshing flow. There's these pressure oscillations set up waves across the combustion chamber that travel at the speed of sound. And there's a corresponding compression behind each of those waves, corresponding to a peak in the pressure that raises the temperature locally. And then this that you see here is the pressure measured relative to some baseline. And you can see this is right at the onset of when NOC is started. So we're looking at the spatial variation of pressure in the chamber here. Remember that everything we've said so far implied that the pressure is uniform in the combustion chamber. But when you have NOC, you can have autoignition occurring in one place in the chamber, which then sets off an acoustic wave, which, if it's resonant, can grow in magnitude and essentially bounce back and forth across the combustion chamber walls. Anyway, you'll see that in the movie here. So you see those waves bouncing across the chamber, and then the amplitude dying down as we get into the expansion stroke. I'll try to show that one more time. So one of the things that we're working on right now is to try to characterize the heat transfer associated with these very high velocity convective flows that are originated by NOC. And if you look at our simulation results, you see huge increase in heat transfer by virtue of this process. Of course, that can lead to engine damage, right? So, okay, so to sort of summarize this first hour, what I think I've shown you is that CFD modeling is able to describe both diesel and spark ignition combustion over a wide range of conditions. Diesel combustion or mixing controlled, premixed combustion also are adequately represented without requiring detailed subgrid scale turbulence interaction to be modeled. Obviously, those processes are important in certain cases, but we use our empirical flame speed, our turbulent flame speed model to encompass what goes on with turbulent chemistry interactions for propagating turbulent flames. The effect of turbulence on combustion is modeled satisfactorily using this G equation type of model that's coupled with chemical kinetics. And as I showed you, you get very similar results with and without considering flame propagation when you have diesel combustion. One of the things we notice is that the use of a flame propagation model in diesel combustion does allow you to get a little more information about lifted flames. You don't see that with just using the kinetics calculation. Flame propagation dominated premixed charge spark ignition combustion requires that you specify a turbulent flame speed in this G type of model. We've given this model a name, call it gamut, the G equation for all mixtures, a universal turbulent combustion model. And it allows you to basically cover diesel type combustion, premixed combustion, and turbulent flame propagation combustion. Then you can use that for both diesel ignition and looking at things like SI engine NOC. So I'll take some questions now before we start on the second hour. Yeah.
So you had the picture where you were showing pressure oscillations, and you said that you needed a small enough time step to capture those pressure oscillations.
Right.
How were you able to differentiate the results you were getting? I guess what I'm trying to say is there an effect of your time step on what the solution is? You know, the sensitivity
Right.
of the solution to time step versus the ability to capture it.
So here we're changing the time step from 10 microseconds to 0.1 microsecond. First thing is that if you look at the number of crank angles that are represented by, say, 10 microsecond, it sort of tells you what frequency you could expect to see in these pictures. So you need to have a small time step in order to get those high frequency components. But if you compare the results, which I haven't shown you here, of 1 microsecond and 0.1 microsecond, you get very similar looking energy spectrum. Obviously, you're going to see discrepancies when you go out to the very high frequencies, because they're just not resolved when you use a larger time step. We made sure that it was not a time step issue that we were looking at. But if you use a long time step, you smear over all of this, you don't see it.
Just related to that question, I guess if you wanted to capture that experimentally, you'd be using a Kistler pressure transducer. It's just 1 microsecond resolution.
Exactly. That's a problem. Typically, in our facility, we have 10 data points per crank angle as the best transducers that we have. And that's, borderline for looking at stuff like this. Yeah.
Would you see that in a HCCI engine?
Yes, as a matter of fact, we've just finished doing some experiments where if you increase the equivalence ratio or the load sufficiently, you start to see those oscillations even in HCCI. And then you see a corresponding increase in heat loss, as I mentioned, and that just complicates the whole matter. The engine efficiency drops off really fast. Yep.
To control NOC in HCCI, there was discussion that you could get an octane boost by injecting ethanol.
Absolutely.
So is there any studies being done with that? And how does that affect your homogeneous charge?
Sure. You're kind of preempting what I'm going to be talking about next, dual fuel combustion. But the MIT group has actually proposed using injection of ethanol at high load to increase the octane number of the fuel, specifically to reduce NOC tendencies. So you'd have two fuels, gasoline and ethanol. Okay, one more.
I'm interested to know if you think using a Fleming approach to diesel modeling would be a reasonable thing to do, especially when you're dealing with multi-phase.
Yeah.
It's just sufficient to go with auto-ignition.
Yeah. So there's a lot of research going on in this area. One of my colleagues, Chris Rutland at the University of Wisconsin, is looking at LES models and combining them with advanced turbulence models. And, they do better. There's no question. But generally, there's more expertise required to run those models, more calibration. So what I always try to do is pick the simplest model that gives good results, because ultimately we want industry to use these codes to design engines. And so the codes have to run very efficiently. We can typically simulate an engine on a standard PC in less than a day. And that's important for people in the industry. As you add more complexity in the models, you learn more, but then they become less useful to designers. Yep.
Is the G equation in ChemKin right now, or is that like?
No, that's something we added to the code. Yeah. It is in the Forte code. We've been working with reaction design. They have a CFD code.
So is that something that they're going to be offering in the future, or would we have to?
Yeah, you can get it right now. You can get it from. Okay.
It's still interesting about the knocking phenomenon. In GDR, you try to shape the piston ball. Do you think such a practice would accentuate this kind of behavior, or you would have more fluctuations?
Well, the good thing about GDI, it depends how you do it, all right? But if you don't have fuel out in the end gas region, you're not going to get this type of knock. Is that the reason you get the knock from that fuel is it has a long time to sit and cook, you see, and eventually auto-ignite. Yeah. Okay, I'm going to move on and sort of try to get some way through the second presentation today. Let's see, we take our break at 10:15. Okay, so we just discussed diesel combustion and SI NOC modeling. Now I'm going to talk about kind of using all of these results and a code that we, let's say, have some confidence in to optimize engines. So we're going to say, let's for a moment imagine that we had a perfect code that's able to predict engine combustion. Let's use it to optimize an engine. So there's a lot of work that has been done in optimization, and I've had quite a few students working on optimization over the years. We just released a book on the subject. Basically, if you look at optimization for CFD, it turns out that you don't really have a lot of choices of optimization tools because gradient-based methods and so on are not applicable because we don't have functions that we can take the derivative of. Let's say you're interested in optimizing emissions from an engine. We don't have a nice equation that we can look at. Instead, we have to solve partial differential equations and so on. So ultimately, what we found to be the most effective are genetic algorithms. And one of the nice things about them is that they can converge on a global optimum. They don't get stuck necessarily on a local optimum. And we combine this with response surface methods. And I'll show you some of the details in a minute. So what is a genetic algorithm? Essentially, let's say you're trying to optimize an engine for nitric oxide and particulate. What you'll do is you'll, using your intuition, generate input to a large number of cases that you would then run. So here are all the cases. You then evaluate the results that you get from those cases that you've run and pick a couple of them that appear to perform well. You would then essentially create new cases from those parent cases. So you have a new population. And you repeat this process until eventually you find cases that are, in some sense, optimum. So there is several different ways you can do this. One way is to define a merit function, which essentially measures, in some sense, how strong, how much weight this guy can lift. The other is to say, well, I'm going to have a whole team of these good performers. Some of them are going to be good at picking up weights with their left hand and others with their right hand. So, but a designer might choose only the strongest with the left hand or the right hand. So we give the designer some options. That's called a multi-objective genetic algorithm. And that's what we've wound up looking at most recently. So how do these things work? So imagine that you have a bunch of input parameters, say boost pressure, intake temperature, injection pressure. These are all input parameters to your code. What you can do is convert those numbers into binary strings of length lambda here. And the length of the string depends on the precision that you define for that parameter. So you have a maximum value and a minimum value, and you get a string for, say, boost pressure. So at the end of the day, you have this long string of zeros and ones, which is your chromosome, if you like. And now you send that off and you run it, along with all its brothers and sisters, and you create a new population, or you get some results. You want to make a new population. So you pick the good performers from the previous set of runs, which will be parent 1 and parent 2. And you perform what's called bit swapping or crossover after performing some selection procedure. So for example, at a random place in this gene string here, you cut the gene, and you simply move this over and give it to the parent. So basically create new designs from those good performing parents. And then to add a little bit of spice to life, you allow some of these bits here to randomly change. And in this way, this is one of the powers of the GA, is that you're not going to converge necessarily on a local optimum, because by doing this random mutation, you may be going off into some part of space that is just not covered by the parents. Okay, so that's the basic idea behind these genetic algorithms. So here you see some results where we used the multi-objective genetic algorithm. We ran many, many cases, typically run over 1,000 Kiva runs. And we collect all the results and plot them in a plot that looks like this. This is a 3D plot of gross indicated specific fuel consumption, nitric oxide, and soot. So all the red points you see here are results from those simulations. And by applying some criteria, we can identify good performers. These are the so-called Pareto cases that essentially form a boundary in this plot where they correspond to the lowest values of one or other of these parameters, or good combinations of the parameters. So we're basically simultaneously optimizing many of these objectives. We can pick any of these blue ones and confidently say that they are an optimum in some sense. So to get further than that, we can take all of that data and apply a response surface method to that data. So for example, if we were just interested in NOx, we'd take all this data and plot NOx versus parameters of interest in the simulation. It might be swirl ratio or piston bowl diameter, whatever it is. And we'll find, again, that we can minimize NOx by operating at a certain place in this map. So that's the idea, is to essentially combine the genetic algorithm with some sort of regression technique to look at the variables themselves. So one of my former students, you guys know, Caroline Genzale, put together this example here of piston bowl design. So we were interested in designing the bowl of a piston in the diesel engine. Some of the parameters that were of interest were geometry parameters, so there are 7 of those. First one being the height of the central pip. We're just looking at one sector of the chamber here of a I think it's a 6-hole injector, 60 degrees. This looks more like an 8-hole. So 45 degrees sector. We're interested in the height of the central pip of the piston, the bowl diameter, the bottom of the bowl diameter, and then several curvature control points where we fit Bezier curves between these control points to define the shape of the bowl. And then we're interested in the injector spray angle. That means relative to, say, the head here, how deep or shallow does this injector-oriented spray, and then the swirl ratio. So basically we have all of those parameters are going to be input parameters to this simulation, and we want to pick out of all of these ones that give the best performance in terms of engine fuel consumption and emissions. We want to optimize NOx, soot, and fuel consumption. So here shows the citizens. In other words, each of these data points corresponds to a run. I should point out that often there's runs outside these pictures here because sometimes we pick cases that are really crazy and they give really crazy results. But these are all cases that have reasonable values of soot, NOx, and fuel consumption, for example. These blue ones are interesting ones in that they fall on this Pareto surface. And the yellow ones are ones that were particularly interesting, and they're shown here. So one of the first things that you can see by looking at the results is that it seems to be a trend where if you increase the swirl, you find that you can reduce the soot, the soot. So for example, relative to a baseline, the soot actually increased for the low swirl ratio, but decreased for the high swirl ratio. But unfortunately, when you decrease the soot, you don't see the same type of big decrease that you saw in NOx. So there's a compromise as you change that particular parameter. And you see there's also compromises in the fuel efficiency. Here you have an increase in fuel consumption, here a decrease. So that you really don't have the whole story here. You don't know whether it's just swirl or is the bowl geometry, or notice here you're injecting deep into the bowl, whereas here it's a more shallow injection. So you want to find out a little more about why these results perform the way they do. So now you use the regression. So this shows a set of regression plots that you get from all of those simulations. Again, we're looking here at soot, just as one of the parameters of interest, as a function of, say, the angle of the spray, the swirl ratio, the bowl diameter, and bowl depth, and spray angle in that last plot. And by looking at this, you can see for as far as soot is concerned, spray angle is kind of important, right? Because you can see there's a minimum over here in soot production if you have a spray angle around 70-something degrees. So that's, from a design standpoint, very important information. Secondly, you can see that swirl ratio is also important. We saw that before. If we increase the swirl ratio, we decrease soot. But bowl diameter has the trend that if we increase the bowl diameter as a percentage of the bore, we can also decrease the soot. And that's well known in heavy-duty engines. They typically have a large bore. On the other hand, the pip height really doesn't play a role. No particular dependence on that. So that we can get rid of that variable right away. Okay, so basically the regression, once you've identified those good cases, you can essentially use them as central points for these regression analyses and look at what happens as you change things around those points. So we see, for instance, an optimal spray angle is predicted here. This is a case where we reduce NOx and soot and fuel consumption from our baseline. We want a nice spray angle around 70-something degrees. The swirl ratio we saw was able to enhance soot reduction, but only near the optimum angle. If we had done the same increase in swirl ratio at a narrower angle here, we would have actually seen soot increase. So basically this conclusion that the spray angle, or that say swirl ratio is important for reducing soot, only applies for a certain orientation of spray angle. And that's what I just said. So you can see the power of these optimization tools, and they can be used then to look at concepts that you would not be able to think of yourself, and I'm going to show you an example of that soon. We were interested in optimizing low temperature combustion, so I'm just interested, I just want to show you a little bit about low temperature combustion as a preview. We already discussed premixed charge compression ignition, early injection, where we inject, say, between 30 before and 12 before top dead center. We see we have a nice premixed mixture, but unfortunately it goes off with a bang. So there's some limits to this. It really only works at light and moderate loads, and we need quite a bit of EGR to dilute the charge. Here's standard injection between 12 and top dead center. This is standard diesel. It's characterized by, let me show you this, high soot, whereas for the early injection case, low soot. The early injection case, on the other hand, has high NOx, but because we use high EGR, we can bring that NOx down. And if we look at late combustion, so-called modified kinetics combustion, injecting after top dead center, you can get something that looks very similar to the early injection case here. And in fact, this has both low NOx and low soot. But combustion stability is an issue here, because if you miss the appropriate combustion timing here, you can get no combustion at all if you inject too late. So a lot of challenges with operating engines in these low temperature combustion regimes. So the first thing we did when we wanted to look at low temperature combustion was to say what type of fuel would make a good fuel for low temperature combustion. And we did some HCCI simulations using different EGR rates and PRF, or isooctane N-heptane blends. And we did this at 1 engine speed and 3 different loads. What I'm showing you here is the result for 6-bar IMEP. This is homogeneous charge compression ignition. And what we plotted here is the indicated specific fuel consumption. Basically, you'd like to operate in regions that are nice and blue here for high fuel consumption. Red is poor fuel consumption, and if you go beyond that, you actually misfire. You don't get combustion. The other interesting thing is the stars. The smaller the star, the smaller the pressure rise rate. So basically, you're kind of walking a tightrope here. If you go far into the blue region, you get very high pressure rise rates, which is not of interest, but relatively low fuel consumption. So you kind of want to be in this light blue region here where the stars are small. Okay, so what this shows you is that if you have diesel fuel with a PRF number of around 20, in order to be in that region, you have to run with EGR rates around 55–60%. On the other hand, if you had a fuel that was more like gasoline, say with a PRF number of 70–75, you have the possibility of operating with very low EGR rates. Now, EGR is expensive in an engine. You have to send that air back, complex air management technology. So and it also costs you in boost pressure. So you really want to try to operate with as low EGR as possible. And so there seems to be an advantage to going to a fuel that's somewhere between diesel and gasoline from the standpoint of this operation. And that's already known from people that have done experiments with HCCI. They found that it operates best with fuels that have octane numbers below that of gasoline and C10 numbers below that of diesel. So here's the 9-bar operating point. You see everything gets squeezed up here. Now your region of no operation is occurring at higher PRF numbers. Again, if you're running with diesel, you can see that to get to the small stars here, you're going to need a lot of EGR. But now you want actually a higher PRF, which would mean more gasoline. And then if you go to the 11-bar point, you see that now you really want to have a lot of gasoline, in other words, close to PRF 100. You're going to need some EGR in order to get to the low pressure rise rate point. Okay, so HCCI, as I mentioned to you before, is limited to light loads. And if you look at these pressure rise rates, they're actually very, very high. And really would not be practical. So the thought was, could we somehow get this effective plot here, but with lower pressure rise rates, by instead of pre-mixing the two fuels to create a certain PRF, in other words, pre-mixing diesel and gasoline, could we do it by injecting the fuels or separately injecting the fuels and doing the mixing in cylinder? So our idea then was, all right, we're going to have pre-mixed gasoline, and then we're going to directly inject diesel fuel. We're going to use a traditional diesel injector, and we're going to use the multi-objective genetic algorithms to see what we can do in terms of getting a reasonable fuel-air mixture distribution. We're going to choose PRF 65 because that gave us good results from the HCCI simulations, and an EGR rate of 50%. And the idea here was we were going to allow 2 diesel injections, an early injection, and we're going to even allow the injection pressures to vary over a wide range from 100 to 1500 bar and be different for the 2 injections. We're going to have injection timings that go all the way from intake valve closure up to close to top dead center, and this one, the second injection, up to 30 degrees before top dead center. And we'll allow basically the amount of fuel in the 2 injections to go from all the fuel in the first injection to all the fuel in the second injection. And the objectives in this case are to minimize the amount of fuel that accumulates on the walls of the combustion chamber or the piston surface, and to see what we can do about controlling the homogeneity of the mixture of the two fuels. So we ran these simulations, 21 generations with 24 members in each generation, and got this set of results. So the solutions are these black triangles, and we identify these Pareto solutions that have nice small amounts of wall film associated with sprays impinging on the surfaces of the combustion chamber. And out of all the results, we could pick several of these Pareto surfaces, but we picked one that seemed to have reasonably good results. Only less than 0.5% of the fuel was in the nature of a film of fuel on the walls of the chamber. And the PRF inhomogeneity, which is measured this way, here's the PRF number of each computational cell. Here's the global PRF that we set to 65. And we looked at the standard deviation. And that gave us a measure here of sort of the best mixing that we could do of these two fuels. It wound up wanting relatively low injection pressures, especially for the first injection, to prevent, which is injected early into a low gas density environment, so the penetration is large. So we wanted low injection pressure here, medium injection pressure for the second injection, and so on. So these results were used then as kind of the input to this concept of running an engine with two fuels. This shows the simulation results. Red corresponds to PRF 100, or just gasoline. So at intake valve closure, we assume the chamber is filled with gasoline-air mixture. And then the two injections that we discussed take place at the injection times that I discussed. We have a first injection that kind of targets the region above the piston here and changes the octane number of the gasoline to an appropriate value. Yeah, I'll talk about that in a minute. And then a second injection that's targeted into the bowl that turns out to be the ignition source. So if we stop the calculation here, this is just at the time combustion is going to occur, we see we have a PRF distribution in the combustion chamber that goes from modified gasoline to modified diesel. The diesel is the most reactive part of the combustion chamber, the gasoline the least reactive. And so what we expect is going to happen is when we compress this mixture, the diesel will ignite first, and we'll have combustion occurring progressively because now we have a premixed mixture. We're not relying on flame propagation. We're relying only on chemical kinetics, but it's going to be phased such that the duration of combustion is determined by the gradient of PRF in the chamber. So to summarize, and we'll take a break now, we have port fuel injection of gasoline, like in your car, cheap injection system. We have direct injection of diesel fuel with a low pressure injector. We inject that diesel fuel in several pulses. In this study, it was 2 pulses. In some of the work we've done since this, we've increased that to 3 pulses. The first pulse basically conditions the fuel in the squish region. The second pulse conditions the fuel in the bowl and serves as the ignition source. So, when we first proposed this, and I'm going to show you some interesting experimental results after the break, people said, oh, you're going to use 2 fuels in an engine. No one is interested in that. And then we reminded them that actually that's what they're already using. In the diesel industry, they're using diesel fuel and SCR, which relies on so-called diesel exhaust fluid, which is a fuel. They don't like to call it a fuel, but it's a fuel. So they're basically using 2 fuels. The advantage of what we're proposing is that these fuels are widely available. And you can imagine getting them readily at pretty much any gas station. So I'm going to show you, after the break, experimental results first obtained from our lab using this strategy, and then I'll talk about some implications of this as we move on. So let's reassemble then at 11:15.